Welcome back to Very Ordinary Differential Equations. In this video, we begin learning about a technique known as substitution of variables, and specifically at first, we approach something known as Bernoulli equations. Well, what's a Bernoulli equation? A Bernoulli equation is a first-order, non-linear differential equation of the following form. Y prime plus some function of x times y equals another function of x times y to a power. So on the right, we have this power of y, which hasn't shown up before, and that's what makes it a nonlinear differential equation. If alpha happened to be 0, if we just had y to the 0 on the other side, we would just have a linear differential equation, y prime plus p of xy equals g of x. Y to the 0 would be replaced with 1, that wouldn't be a problem. Also, if alpha is 1, we would have a separable equation. Because then, I could replace y to the alpha with just y, and now these are the same power of y, so I could move the p of x over, have g of xy minus p of xy, factor out the y, divide it to this side, and now I have a separable equation. So if alpha is 0 or alpha is 1, this is actually something that we can do already. But for any other value of alpha, the methods we already know are not going to be sufficient. Specifically, try to imagine alpha being something like 1/2. Then I have a square root of y here, which is something we just haven't seen yet. And we attack this problem through the technique of U substitution. So suppose we have the following Bernoulli equation, okay, y prime plus p of xy equals g of xy to the alpha, where alpha isn't 1. If alpha is 1, the equation would be separable and we wouldn't use this technique. So for the sake of argument, try to divide by y to the alpha. Then multiply both sides by 1 minus alpha. I mean, I can, it's not clear why I would want to yet. What you'd end up with is this. Okay, so I divided both sides by y to the alpha. So here I just have a y to the minus alpha. This term already had y to the first, so we now have y to the 1 minus alpha. On the right, we canceled out y to the alpha. And then I multiply everything by 1 minus alpha, and we have something that looks significantly worse. But we're going to do the substitution u equals y to the 1 minus alpha. Now if I differentiate u equals y to the 1 minus alpha, we get u prime is 1 minus alpha, y to the negative alpha. Notice I just have to reduce the power by 1. If I subtract 1 from this power, it becomes minus alpha. And thanks to the chain rule, another y prime, which happens to be exactly the first term we have here. So performing various substitutions, we would get this. So now this was exactly u prime. I have a 1 minus alpha and a p of x, but y to the 1 minus alpha was exactly u. So now we have u prime, a function of x with a constant out in front, times u, equals a function of x with a constant out in front. So since 1 minus alpha is a non-zero constant, remember that alpha wasn't 1, this is now an inhomogeneous linear first-order differential equation. The derivative of u plus a constant times a function of x times u equals a constant times a function of x. Straightforward, first-order, linear, inhomogeneous differential equation, and that can be solved using other techniques. Overall, just to refresh, if you have a differential equation of the form y prime plus a function of x times y is a function of x times y to a power alpha. If that power is 0, you typically wouldn't even bother writing y to the 0, but what you would have is a straightforward inhomogeneous linear first-order equation. Y prime plus p of xy equals g of x times 1. Go ahead and solve it. If alpha is 1, you have the same power of y in two places. By collecting like terms, you can actually separate variables, and this is separable. So go ahead and solve it that way. Otherwise, do the substitution u equals y to the 1 minus alpha, and then you end up with this equation right here. U prime plus a constant times p of x times u equals a constant times g of x. You can solve that because that is a linear inhomogeneous equation. Now once you solve for u, go ahead and replace. Okay, remember that u was y to the 1 minus alpha, which means that y is u to the 1 over 1 minus alpha. Let's see this technique in action by finding a general solution to the Bernoulli equation y prime plus y equals xy squared. We directly have the form we want, where we have y prime plus a function of x times y equals a function of x times y to the alpha. Specifically, p of x is just 1, g of x is x, and the alpha is 2. So with alpha equals 2, we need to perform the substitution u is equal to y to the 1 minus alpha. Now 1 minus alpha is minus 1. So we're going to perform the substitution u equals y to the minus 1. And when you perform the substitution, you're going to end up with u prime plus 1 minus alpha p of x u equals 1 minus alpha g of x. So this is the formula from the previous slide. So we just have to go through and compute u prime 1 minus alpha p of x u, 1 minus alpha g of x. Now 1 minus alpha is just negative 1. So we end up with u prime minus p of x, but p of x was 1. So 1 minus alpha p of x becomes negative 1 times 1, so minus u. And over here, 1 minus alpha was minus 1, negative, and g of x was x, so there it is. That's just the formula from the previous slide adapted to this problem. Okay, now we have a linear first-order inhomogeneous equation. How do we solve that? We begin by solving the complementary homogeneous equation, u prime minus u equals 0. Okay, this directly gives us a single solution. Notice that if you move the u over, you get u prime equals u, and we all know the solution to that is that u is e to the x. Okay, you can also just solve it using the techniques that we learned earlier. So we've performed the substitution, u is y to the minus 1. That gave us a new inhomogeneous linear first-order differential equation. We found a single solution of the complementary equation. We'll call it u sub 1, and that's just e to the x. So now what we need to do is perform our variation of parameters. I don't want to use the letter u because we're clearly using that for something already. So let's find a particular solution u sub p equals v times u1, where v has to be the integral of f of x over u sub 1 of x. Okay, and in our equation that we have now, f of x is negative x, and u sub 1 was e to the x. Okay, factoring the minus sign out in front and bringing this e to the x into the numerator with a negative exponent, we have a fairly typical looking power of x times exponential. We integrate that fairly quickly, and it's just x minus 1 times e to the x. So we have found a particular solution of this thing, x minus 1 times e to the minus x, times our existing solution e to the x. Notice I now have an e to the x times x. Those cancel out. So one particular solution is just given by x minus 1. All right, what have we done so far? We began by doing the substitution u equals y to the minus 1. That gave us a new differential equation. But this new differential equation we have here is a nice linear first-order inhomogeneous equation. How do we solve that? Find one solution to the complementary equation. We got e to the x. You also have to find a particular solution to the inhomogeneous equation, and we got x minus 1. Therefore, all solutions to this differential equation in u are given by u sub p plus any constant times u sub 1. In other words, x minus 1 plus a constant times e to the x. But this is now a solution in terms of u, and we wanted originally a solution in terms of y. But if u is 1 over y, then y is 1 over u. So here is u, it's x minus 1 plus a constant e to the x, which means y is 1 over all of that. 1 over x minus 1 plus a constant times e to the x. There we have it, a solution to the differential equation we began with, the Bernoulli equation y prime plus y equals xy squared. Solutions must be this function here, where c is any constant. Let's take a look at a second example. Let's solve the initial value problem. Y prime plus y over x minus the cube root of y is 0, but also y of 1 is 0. Well, we need to make it look like a Bernoulli equation. So explicitly, we say y prime plus 1 over x times y equals the cube root of y, and I'm expressing that cube root as a power of 1/3 just for clarity. So we're going to do the substitution. U is y to the 1 minus alpha. Now 1 minus 1/3 is 2/3, so we're going to do the substitution. U is y to the 2/3. We then check our formula, and we get the following equation. U prime plus 1 minus alpha, and again 1 minus alpha is 2/3, times this function 1 over x times u equals 1 minus alpha times g of x. 1 minus alpha was 2/3, and g of x, well, the function of x on this side is just 1. So that formula spits out u prime plus 2 over 3xu equals 2 over 3. So there's our new equation of u. It's a linear first-order inhomogeneous equation. So solve the complementary equation. U prime plus 2 over 3x u equals 0. Okay, so if we have u prime plus 2 over 3x u equals 0, we need to take e to the minus integral of 2 over 3x. So that's minus 2/3 log absolute value x. Of course, now I have an exponential combined with a log. Those are going to cancel out. So a single solution to the complementary equation is absolute value of x to the minus 2/3. In the original equation, though, notice that x equals 0 is definitely a discontinuity. Way at the beginning, I have a division by x here. So any solution we found can't exist at 0. It's either going to exist for positive x or for negative x. Look at our initial value. Our initial value is for a positive x. So let's assume we're only dealing with positive x's. Okay, we can't account for 0 anyway. And since we have to account for x equals 1, let's just say we've got positive x's going on. In that case, the absolute value becomes unnecessary. Absolute value of x is just x. So a single solution to the complementary equation is given by u sub 1 is x to the minus 2/3. All right, so we performed our substitution. We got a new differential equation, and we got a solution to the complementary equation, x to the minus 2/3. Now we need to find a particular solution. U sub p is vu1. By solving, v is integral of the function of x on the right-hand side, that's 2/3, divided by the particular solution we found, that was x to the minus 2/3. Well, this constant of 2/3 I'm going to factor out. Bring this power of x up into the numerator, it becomes positive. This is now a pretty straightforward anti-differentiation problem. 2/3 times x to the 2/3 is 2/5 x to the 5/3. Plus an arbitrary constant, but remember in this technique that constant can always just be taken to be 0. Okay, now that we did that integration, one particular solution is given by vu1. That's 2/5 x to the 5/3 times x to the minus 2/3. We combine our powers of x and we just have 2/5 x. Now that we have a particular solution and we found a solution to the homogeneous equation, we know that we have found all solutions to our modified equation, the one here. All solutions to this are now given by up plus a constant times u1, in other words 2/5 x plus a constant times x to the minus 2/3. So we did our substitution, we got a new differential equation, and we found that all solutions are given by u equals 2/5 x plus a constant times x to the minus 2/3. The only thing that remains is to solve for y. Now if u is y to the 2/3, then if I raise both sides to the 3/2, I recover y, and I just get u to the 3/2. So if u is all of this, well then y is all of that to the 3/2 power. So the initial value problem, we haven't attacked yet, but the differential equation itself, the one we started with up here, is solved by y equals 2/5 x plus any constant times x to the minus 2/3, all of that raised to the 3/2. Okay, so we have found that the differential equation we began with is solved by y equals 2/5 x plus a constant times x to the minus 2/3, all to the 3/2, and we can finally move on to our initial value. When x is 1, we know that y is 0. That was given up here. X being 1 spits out y equals 0. So to get a 0 out and plugging on x equals 1 in, this would be 2/5 times 1 plus c times 1, all raised to this power should equal 0. Therefore, that constant must have been minus 2/5. So we have found that c is minus 2/5. Therefore, our single unique solution to the initial value problem is given by y equals 2/5 x minus 2/5 x to the minus 2/3, all raised to the 3/2. Let's do another example. Solve the equation y squared y prime plus y to the 7th over x squared equals y cubed over x squared. Looks like a mess. All of the standard forms that we've worked with have y prime by itself. So the first thing we want to do is divide by y squared. That transforms this to y prime plus y to the 5th over x squared equals y over x squared. Now we can more easily see that this is a Bernoulli equation, but we were supposed to have y prime, then a y, and then y to the alpha on the other side, so we move some stuff around. Y prime minus 1 over x squared times y is minus 1 over x squared times y to the 5th. With alpha equals 5, we're going to do the substitution u equals y to the 1 minus alpha, and 1 minus 5 is negative 4. So our equation becomes u prime plus 4 over x squared times u equals 4 over x squared. Okay, so remember, you're just going to get a u prime here. You have a 1 minus alpha times the function of x times u, and 1 minus alpha was negative 4, so that became positive. And over here, this negative times the 1 minus alpha became 4 again. We still have the 1 over x squared, and the y to the 5th was exactly divided out. Okay, so now we have a new linear first order inhomogeneous equation, but in a variable u. So here is our equation that we have. U prime plus 4u over x squared equals 4 over x squared. We begin by solving the complementary equation. U prime plus 4u over x squared equals 0. So what do? We integrate 4 over x squared, put a minus sign out in front, exponentiate it, and we end up with e to the 4 over x. So there is a solution to our complementary equation. Then we have to find one particular solution, up equals vu1, where v is the integral of this function 4 over x squared over the single solution to the complementary equation that we found, e to the 4 over x. So we have to integrate this. Okay, notice that a u substitution takes care of this quite nicely. If u is negative 4 over x, well then du is 4 over x squared dx, so that worked out nicely, and we don't need a constant of integration in this technique. So a particular solution is given by v times u1. v was e to the minus 4x, u1 was e to the 4x. A particular solution is 1. This might look a little weird, but if u is the constant 1, come back to this right here and notice that u prime would be 0, 4 over x squared equals 4 over x squared. So indeed, a particular solution is given by u just being constantly 1. So we found a single solution to the complementary equation, e to the 4 over x, and we found a particular solution 1. Therefore, all solutions are given by our particular solution plus a constant times the solution to the complementary equation we found. So u must be of the form 1 plus a constant times e to the 4 over x. Now that we know u is of the form 1 plus a constant times e to the 4 over x, we can solve for y. Okay, if u is y to the negative 4, then y is u to the minus 1/4, so y is u to the minus 1/4. There it is, 1 plus a constant times e to the 4 over x, all raised to the minus 1/4. All right, all together, what did we do? A Bernoulli equation is a first-order nonlinear differential equation in a very specific form. Y prime plus function of x times y equals function of x times y to the alpha. It's notable because it's a nonlinear differential equation and we can actually solve it, which is not going to be something we do very often. All you have to do is perform the substitution u equals y to the 1 minus alpha, which yields the following first-order linear inhomogeneous differential equation. Solve that using earlier techniques, and you'll get some expression for u, which you can then recover in terms of y.